It is assumed that the resting metabolic rate RMR of healthy males in a complete silence is 5,710 kgs per day. Researchers measured the RMR of 11 healthy males who were listening to calm classical music. The data are given in kgs per day. So the data is there below. So part A asks, assuming the RMR is normally distributed in the population, is there significant evidence to support the claim that the mean RMR of males listening to calm classical music is different than 5,710 kg per day? Use the 0.05 level of significance. Test the claim using the classical approach. So the first thing we do is go in and enter our data. So a good habit is to do second plus 4 and then enter. I'm not going to do that. I've already entered my data in, but you would do that to clear out any list you had. And then stat, enter, and then you're going to type in your data values. So I've already typed it in, so you can pause it, type in your data values. So notice when I go down the last one, this was L1 12, so also now I've typed in 11 data values. So now that we've typed those in, again, we're going to go through it and write down our values here. So we only have 11, but we're coming from a population that's normally distributed, so we're good to go there. So let's write down our null and alternative hypotheses. So we're looking at mu, and that was always equal to, and this is 5, 7, 10, and they want to know is different. So this is going to be not equal to, right? So we're going to do a t-test, because we're working with a mean, and we don't know the population standard deviation. So we're going to do stat, test, t-test, but we have data this time, so we're going to do our input as data. And mu naught is going to be 5, 7, 10. Our list is L1 or wherever you put your data. Our frequency is going to be 1, and then mu is going to be not equal to mu naught, and then press calculate. Oops, too many places here. So I'm going to go ahead and write down T, our test statistic. I'm going to round this to 4 decimal places in our p-value, and I'm going to go ahead and round that to 4 as well. So 0.9978, just so we have those, right? And you'll notice it also computed the mean and standard deviation for those samples. So, draw out our curve here. And we have 2 critical regions that's dealing with a two-tailed test. And a t-test, so we have a t-distribution, so negative t sub alpha over 2 and positive t sub alpha over 2. And we want to take our alpha, which our probability of making a type 1 error, and split it in half, and that tells me how much is in each of our tails here. So 0.025, and then in the middle, if I do 1 minus 0.05, I have 0.95, and then we will need to look at our degrees of freedom. So our degrees of freedom is our sample size, which is 11 minus 1. So our degrees of freedom is 10. And then the area in the right tail is going to be the 0.025. So these are our important values here. So if we go to our table and we look at 10 degrees of freedom, and 0.025, we get 2.228. So we have 2.228 and negative 2.228. And then our test statistic is just slightly past the center. Right? So since our test statistic is between the critical values, or not in the critical region, we do not reject the null hypothesis. Okay. So now we want to test the claim using the p-value approach. So we're going to compare the p-value to alpha. So our p-value is 0.9978 and alpha is 0.05. So our p-value is greater than alpha. So since our p-value is greater than alpha, we do not reject our null hypothesis. As you can see, we're getting the same conclusion no matter what result we use. And then lastly here, we want to test the claim using the 95% confidence interval. So here we're going to do T interval. So stat, test, and then T interval. And our input is going to be data. And our list is in L1. Our frequency is 1. And our C level is 0.95. I'm just going to go down to calculate, and our interval here is 5001.6, comma 6416.5, and mu naught was 5710. So since 5710 is between the lower bound and upper bound, we do not reject the null hypothesis. So you can see no matter what approach we use, we still get the same result.